Now, this whole thing is really a big deal. When does a set of multiples of a set, a sum of multiples of a set of vectors equal some other vector? What kind of vectors can you get from a set of vectors by adding multiples of those vectors? Now, the big idea here, this part of that, a subset of that idea, and one you have to understand is, okay, just the mechanics of determining whether this is possible comes down to the fact that a sum of multiples of V1 and V2 can be written C1 V1 plus C2 V2, and that the sum of multiples equals some other vector is this equation. And this equation then becomes what? It becomes a system of two equations with variables C1 and C2. Or it becomes an augmented matrix for that system. Or it becomes a matrix solvable for C1, C2 by inverse matrix. Now, the numbers that you get in the matrices in the system are pretty much the same, but it looks different, and we solve it a little bit differently in every case. Now, solving the system can be done by the same steps you would use in solving the augmented matrix and vice versa. Okay, another thing is, you can do this for more than two vectors, and they don't have to be in two-dimensional space. So this equation just says that a linear combination of the vectors V1, V2, V3, V4, etc., up to V sub n, where n is how many vectors you have. So if you have a set of 17 vectors, n would be 17. Okay? It's not an infinite set. These dots don't mean it's infinite. These dots mean it keeps going by the same pattern until you get to this, whatever n is. So this could stand for 100, a combination of 100 vectors, a sum of multiples of 100 vectors. That equal to some vector. This becomes a system of how many equations in C1 through Cn. Well, how many equations depends on how big these vectors V1 through Vn are. If these are column vectors with 10 numbers in the column, then you would get 10 equations. You can think about why. You might not totally see it, and we'll say it very explicitly when we get to it, and you will see it, but if you see it now, that's even better. Okay, so how many equations do you get? Well, if you had, if these vectors each had 10 numbers, meaning those vectors would be of dimension 10, and there were 17 of them, then you would have more vectors than you have equations. Okay, and you would have your augmented, well, let's say your matrix equation would not be a square matrix. So you couldn't solve by inversion. But still there might be a way to solve, and your augmented matrix might be the way to go. So I'm just mentioning this to tell you that you just extend what you do in 2 dimensions to whatever number of dimensions, and it works the same way. You have to know how to interpret the results that you get, and we have to build that up kind of slowly. But it's the powerful aspect of linear algebra is that you can work in any number of dimensions. You can't sketch things in any dimension higher than 3. You can certainly make a 3-dimensional sketch. It's a little tricky. And it takes a lot of practice to get any good at it. But in 4 dimensions or above, you can't sketch it. But you can still do the algebra. You can still solve the equations. Okay, you can still do everything. Okay, so, the next problem that we didn't take time to complete in class because we didn't have time to complete it, was you were given 3 vectors, and there are 3 vectors, each with 3 components, and you have the same kind of equation. So what you did in 2 dimensions, you need to do now in 3 dimensions, with vectors in 3 dimensions, and there are 3 of them. Okay, well, I'll do this in the next video, and we'll see how that works out.